Hi everyone, my name is Bo Tan. I'm a file system engineer in the Teradata organization. Today, I will be presenting the TechBytes for the Snapshot MI or Master Index Mirroring feature. The target audience of this presentation are DBAs, Teradata database support personnel, and anybody else interested in learning about the Teradata database file system or this feature in particular. Amongst its many strengths, the Teradata database prides itself on its high reliability. Features such as RAID and fallback provide a strong backbone for fault tolerance that allows the system to be highly available. Unfortunately, hardware and software do occasionally fail. The Teradata database is constantly looking for opportunities to avoid any type of database restart by isolating faults and, when possible, automatically repairing data from fallback. However, in cases where the fault is too severe, a database restart is inevitable. Long database restarts have the potential to cause a huge disruption to customer systems. When database restarts happen, it is in the best interest of the customer for the system to start up as fast as possible. This feature, Master Index Mirroring, is a Teradata 16.0 feature that will reduce restart times on a system with large amounts of permanent data and further improve data protections. The feature also covers planned restarts, so customers do not necessarily need to encounter a failure to benefit. First, a very brief overview of the Teradata file system and this feature. The master index, or MI for short, is the top level of the multi-level Teradata database file system B tree. Before this feature, the MI always resided in memory and was never written to persistent storage. This top level of the B tree was rebuilt on all restarts that did not preserve the file segment cache, otherwise known as the FSG cache. One common type of restart that did not preserve the FSG cache would be the case where the Teradata database was shut down completely and then brought back up. A second type would be one where a system administrator intentionally triggers a restart with a command line option to clear out the FSG cache. And a third situation would be one where there is a configuration change, such as when one or more amps or nodes drop out of the configuration due to unrecoverable hardware or software failures, and the Teradata database has exhausted all avenues to keep that amp functional. Starting with Teradata Database Release 16.0 and beyond, the MI will no longer need to be rebuilt on these types of restarts, as it will be maintained as a persistent structure on storage. Restarts will have the ability to read this persistent MI copy, bring it up to date by applying write-ahead logging concepts, and put it immediately into use. As you will see later in this presentation, the time it takes to rebuild the MI increases linearly with the amount of data allocated, and therefore, by avoiding the rebuild altogether, the most noticeable gain will be on systems that host large amounts of permanent data. The savings will all be realized in the initializing DBS vprocs phase of the Teradata database restart. This phase of startup is where the Teradata database's file system is started up. In order to maintain the MI on disk so restarts can utilize it, a mirror is maintained during system runtime. This maintenance is done in the background to reduce overhead on foreground workloads. There will be minimal to no I/O overhead, as the mirror is only written to persistent storage once a minute by default by a background task. The CPU overhead is expected to be noise. On all restarts where FSG cache is preserved, this feature has no effect on restart times, as the MI is preserved in FSG cache across such restarts. This feature is enabled by default when a system is first upgraded to 16.0 or upon installing a new 16.0 instance. Master Index Mirroring supports a couple of key Teradata initiatives. First, the recent big data trend means that our customers are storing more and more data in the Teradata database. Since Teradata file system restart times have a direct linear correlation with the amount of data on a system, we saw an opportunity to eliminate the MI rebuild. This would allow us to break this correlation and make restart times more constant. Second, some new storage technologies that are already here or on the horizon either emphasize an increase in capacity or are specialized for code data with slower I/O read speeds. Since rebuilding the MI requires reading all the second-level index structures, the cylinder indices, or CI for short, these new technologies would further extend the amount of time needed to complete an MI rebuild. Here, we again saw an opportunity where avoiding an MI rebuild would help customers, as it would make it easier to integrate these new technologies without having to suffer through longer restart times. As a result of seizing these opportunities, our customers' system availability will increase, as the time the system takes to recover from a restart is noticeably reduced especially on systems with lots of allocated permanent data. To understand the improvements introduced by this feature, let's first look at how the MI was built prior to Teradata Database Release 16.0. When the file system first starts up, the MI is created. The file system will read the cylinder index of all cylinders with persistent data into memory, create a cylinder index descriptor, otherwise known as a CID, and insert it into the MI based on logical table and row order. This CID has information describing the entire cylinder, such as the logical table and row ranges of content stored within the cylinder, sector usage within the cylinder, and any other information necessary to manage the cylinder. After all CIs are represented by CIDs in the MI is marked as ready for use. As you can see, building the MI is significantly I/O bound. The time it takes to complete the MI rebuild is linearly proportional to the amount of permanent data on the system. Therefore, systems with large amounts of allocated data will experience the longest MI rebuild times. Some of Teradata's biggest systems have many tens of thousands of allocated cylinders per amp, and reading the CIs from each of those perm cylinders can often take upwards of minutes for the MI rebuild operation to complete. On bigger systems, 2-minute MI rebuild times are common, and on the largest systems, 5 or more minutes is not unheard of. This trend will only worsen as big data trends continue. Now, with Teradata Database 16.0, the MI no longer needs to be rebuilt in cases where FSG cache is lost across a restart. Let's first look at how the MI and its new mirror is maintained during system runtime. The Teradata file system would have created the MI as well as the MI mirror during system startup. It would also have created the 2 background tasks that are shown on this slide. These 2 background tasks are not new to Teradata Database 16.0, as they existed prior to maintain the log for write-ahead logging purposes. In Teradata Database 16.0, they have the added responsibility of maintaining the MI mirror. Now, let's see what happens when a task makes any modification that requires a CI update. The CI is read in if it's not already in FSG cache. The CI is updated, and the CID that describes the CI is also updated in the MI to match. The foreground task sends a delta describing the change made in the CID to the first background task and awaits a response. Now, while waiting for an acknowledgement, other tasks could be modifying other CIs in the same fashion. Let's assume 2 other tasks have CI modification requests. As you can see, at this point, 3 tasks are held waiting for an acknowledgement from the background task that they have recorded the deltas. Now, the background task wakes up and takes all the deltas, applies them to the MI mirror, and then acknowledges to the 3 foreground threads that the deltas were received and processed. The foreground task now can proceed to finalizing the modifications. Depending on the FSG caching rules, these CIs could stay in cache so that they can be written out later, or they can be written out to disk immediately. The CIs are released so the other modification to those CIs can proceed. This process continues as more CI modifications come in. The MI mirror can gather many hundreds and thousands of updates without ever being written out to disk. Once a minute, a second background task will place a lock on the MI mirror, block all the CIDs together, and write them out to dedicated MI cylinders on disk. Once done, the second background task releases the lock on the MI mirror, allowing further deltas to be applied. As you can see, this established a fairly up-to-date copy of the MI on disk that can be at worst 1 minute behind the MI mirror in memory. One might ask, what are the key benefits of maintaining the MI mirror as a background operation? There are a few. First, the foreground work is less affected as it does not have to worry about maintaining the clone MI and the synchronous events associated with writing it out to disk. Second, by having dedicated background tasks dedicated to maintaining the mirror itself, foreground generated deltas from many concurrent threads can be batched up, applied to the mirror, and written out to disk using a single set of IOs. This is consistent with one of the key advantages of using a write-ahead logging scheme. Now, assume the system restarts and all memory is lost. When the Teradata database starts up the Teradata file system, there will be nothing in FSG cache. The Teradata file system will first create the MI. It will then read all the CID blocks from the dedicated MI cylinders from disk and copy those CIDs into the MI. Applying the concepts of write-ahead logging, the file system startup process will use the records in the wall log to bring the MI up to date. It will then duplicate the MI and make that the MI mirror, and complete other essential parts of file system startup. Finally, the 2 background tasks will be started, and the file system will be open for work. ScanDis is also improved by this feature. Prior to Teradata Database 16.0, filers started up with fatal amps or the database down would have to rebuild the MI by reading all the CIs with permanent data. Should there be a corrupt CI, filer startup would not know how to create a CID and put it into the MI. As ScanDis can only scan data that is in the MI, ScanDis would not be reporting errors in that corrupted CI or anything on that cylinder. With Teradata Database 16.0, the MI is written to disk and brought up to date with write-ahead logging concepts. Therefore, even in the presence of a corrupt CI, a persistent CID would be present in the MI. ScanDis would then be able to scan it and report errors in the CI as well as any content in that cylinder. This feature also improves the ability for the file system to detect lost CI writes during Teradata file system startup. Before Teradata Database 16.0, after a restart with no FSG cache, the first read of any CI would be exposed to non-detection in the case of a lost write. This is due to the fact that the CI's external checksum is stored in the CID. As the MI was lost across the restart, this CID checksum is also lost, and without an external checksum to validate against, the first read of CIs from disk are exposed to lost writes. However, with MI mirroring in Teradata Database 16.0, this improves lost CI write detection. As the CIDs are written to disk and brought back up to date via write-ahead logging, an external checksum is now available to validate the first CI read against lost writes. Some expectations for the feature. Restart time savings is dependent on multiple factors, including the amount of data allocated per amp, the speed and transfer rate of data from storage, as well as the overall speed of the drive. The file system will also revert to old functionality of rebuilding the MI on restarts in a couple of conditions. A. When the restart is triggered during or immediately after low space conditions are detected, where a mini cylinder pack is likely to run. Or B. When the persistent MI copies on disk is found to be corrupt. The file system will maintain 2 copies of the MI in separate cylinders for redundancy purposes. So even if one copy is invalid or corrupt, there's always a second redundant copy that can be put into use. The only time when an MI rebuild is necessary is when both redundant copies is found to be corrupt. Or C. When there could be situations where Teradata support personnel are addressing critical issues with the file system on time-constrained customer incidents. In such a case, they could make repairs manually to the Teradata B tree. This will likely cause filer to automatically invalidate the CID blocks on disk and rebuild the MI from scratch. This concludes the MI mirroring TechBytes. Thank you.